Hey everybody, Dr. A here, and in this video we are going to be exploring an example of drawing shear and moment diagrams using the graphical method. So let's go ahead and get started. Here we're being given the instructions that say use the graphical method to sketch the shear and moment diagrams. Okay. Now in the figure we have a simply supported beam, and if you remember, a simply supported beam is one that has a pin and a roller on the opposite ends of the beam. And this simply supported beam is a total of 3 meters long. It's supporting a uniformly distributed load of 2 kilonewtons per meter, and it has a point load of 300 kilonewtons at the 2 meter mark here. Okay, so if you remember, whenever we sketch shear and moment diagrams, you always start by solving for the external reactions when you're doing the graphical method. So under solution here, we're going to start by solving for those external reactions. You must do that whenever you are using the graphical method to sketch shear and moment diagrams. So I'm going to go ahead and draw a free body diagram of the entire beam, and I'm going to go kind of quickly through solving for these externals. But I am going to show some of my work, so it'll be a nice review for some people who maybe are a little rusty on solving for external reactions. So I'm going to draw the free body diagram of the entire beam with all of the known and unknown reactions and loads on it and the dimension lines. So this free body diagram is pretty similar to the given figure. So we're going to start by saying some of the moments about point B equals 0, and by applying this equilibrium equation we can solve for AY directly. I'm going to say negative AY times 3 meters plus 300 kilonewtons times 1 meter. I'm going to wrap this equation around and say plus 2 kilonewtons per meter times 3 meters times the moment arm, which is 1.5 meters, equals 0. Doing some rearranging, I can get a Y is 103 kilonewtons going up. So if I were you, I would punch this in your calculator if you're a little rusty with solving for externals, and do this along with me and make sure you're getting the same value. Next, we're going to say sum of the forces in the Y direction equals 0. We take things up as positive, and we're going to include in there that AY we just calculated here, and we're going to say 103 kilonewtons, and then we're going to say minus 2 kilonewtons per meter times 3 meters, minus 300 kilonewtons, and I'm going to wrap the equation around, say plus BY equals 0. Do a little bit of rearranging, and we're going to get BY is 203 kilonewtons reacting upwards. And clearly by observation AX is 0 because we have nothing applied in the horizontal direction. So the next thing I'm going to do is I'm going to go ahead and start sketching my appropriate diagrams. Now what I like to do is I like to stack my diagrams on top of each other just to help me see how things line up. So I'm going to scroll down a little bit, and I'm going to just go ahead and redraw the loading diagram that I just calculated the loads for. So that AY was 103 kilonewtons, that BY was 203 kilonewtons, and I have the uniform load here. That is 2 kilonewtons per meter, and I have that point load, which is 300 kilonewtons. And I'm going to go ahead and make sure my dimension lines are sketched on here as well. So I just redrew you know, the loading diagram just to help me line things up. So the next thing I'm going to do is I'm going to go ahead and sketch my axes for my shear diagram, which is going to have units of kilonewtons on the vertical axis, and horizontal axis is X with units of meters. And at this point, if you remember our process, whenever you're sketching the shear diagram, you want to start from the left side and you want to move from left to right across the beam. And you want to ask yourself, what is causing a shearing effect? So a slicing effect through the member. okay? And you want to move systematically from left to right, okay? So I'm going to go through this process, and I'm going to show my work along the way, all right? So starting all the way on the left side, the first thing we encounter is that AY reaction of 103 kilonewtons going up. So the first thing I'm going to say here to show some work is I'm going to say at x equals 0, the change in shear is equal to AY, which is equal to the 103 kilonewtons, which means at x equals 0, the shear force itself is 103 kilonewtons. So what that's going to do is that's going to jump me up to about right here, and that's going to be a value of 103. Okay, now I'm going to systematically move to the right. I'm moving left to right. So the next thing I'm going to write here is I'm going to say from x equals 0 meters to 2 meters. Okay, so then we're going to ask ourselves what's happening from 0 to 2 meters. Now, why am I going from 0 to 2 meters? Why am I not going all the way to the end of the beam, the 3 meter mark? Well, it's because I have this applied 300 kilonewton load here, and so that's going to be an abrupt change, which is going to define a second domain after it, okay? So I need to be mindful of the domains I'm working on. So for now, I'm just going to go from the 103 kilonewtons up to, just up to where I have a new abrupt change, which is represented by the applied 300 kilonewtons. So that's why I'm going from 0 to 2 meters, okay? So from here, I'm going to say the change in shear from 0 to 2 meters is going to be equal to -2 kilonewtons per meter times the length over which it's distributed, which is 2 meters. Okay, now what does that represent? Well, that represents the area of this load diagram. Okay, so I'm going to make a little marker here. This represents the area of the load diagram from 0 up to 2 meters. Okay, and so I punch this through, or I don't even have to punch this through. Hopefully that's -4 kilonewtons. All right, so what does this mean? This means that at x equals 2 meters, but just to the left, infinitesimally to the left of 2 meters, which means just to the left of that 300 kilonewtons, what is our shear force? Well, that's going to be V equals 103 kilonewtons minus 4 kilonewtons, which is 99 kilonewtons, okay? So I have gone just up to the 300 kilonewtons, but I have not gotten to it yet. I'm 1 pixel to the left of the 300 kilonewtons. That's why I have this superscript of a negative sign here. So what that tells me is I'm about right here, okay? So that's the 99 that I got, all right? Now, how are these 2 points going to be connected? Well, they're going to be connected by a linear segment. So that's just a straight line, okay? Linear segment. And the reason is because, remember, we got the area beneath this, this diagram, okay? So that represents the antiderivative or the integral beneath this constant segment. And so what is the integral of a negative constant? Well, it's a linear decreasing value. And when I say negative constant, that's referring to the fact that this 2 kilonewtons per meter is pointing down. Okay, that is what makes it a quote-unquote negative constant, which gives us a linear decreasing antiderivative or shear segment. Okay, so next thing, moving on, we're going to say at x equals 2 meters. Right at x equals 2 meters, the change in shear is -300 kilonewtons. That's just that applied load here. So what that's going to do is that's going to jump us down. That's going to create a jump downwards in the shear diagram, okay? And so that's going to bring us to a new shear value that's going to be actually at x equals 2 meters just to the right. So what is that shear value infinitesimally to the right side of that 300 kilonewtons? Well, it's going to be the 99 kilonewtons that we were just at minus 300 kilonewtons. And of course, that will take us down to negative 201 kilonewtons. So that's going to jump us down to about right here. Let's try to draw this a little bit more to scale, right about there, negative 201. Okay, and again, that negative 201 is just to the right of that 300 kilonewtons. Okay, what happens next? Well, now we are on this second domain that's taking us from 2 meters all the way to the end of the beam, which is at x equals 3 meters. Okay, so I'm going to say next, I'm going to say from 2 meters to 3 meters. All right, we're going to have a change in shear of the area beneath this part of the loading diagram. Okay, so that's going to be negative 2 kilonewtons per meter multiplied by 1 meter. And that, of course, equals to negative 2 kilonewtons. All right, and then what we can say is at x equals 3 meters, but just to the left, we're going to have a shear force of negative 201 kilonewtons minus 2 kilonewtons, which of course that is negative 203 kilonewtons. So that's going to put us right about here, just a little farther down, negative 203. And that is also going to be a linear segment. Again, for the same reason we discussed before, you have a constant loading diagram here that's pointing down, and so you're going to have a linear decreasing shear diagram. And finally, to close us off, we're going to say at exactly x equals 3 meters, you have a change in shear that's equal to by, which is a positive 203 kilonewtons, which means that at x equals 3 meters, the shear will close to 0 because you are saying negative 203 plus 203, which closes you off to 0, which is correct. Remember, your shear diagrams and in a minute, your moment diagrams should always close at 0. That indicates that your system is in static equilibrium. Okay, so that's the shear diagram, and this is all of the work that goes into generating that shear diagram. Once you get more comfortable with this process, you can punch a lot of this in your calculators successively, and you might not need to show nearly as much of this work, but for the sake of learning, I want to show you how I get these values. Okay, let's move on to the moment diagram. Beneath the shear diagram, I'm going to go ahead and draw a moment diagram axis. This is going to have units of kilonewton meters, and we have x in meters here, okay? And I'm going to follow a similar process that I did with the shear diagram. I'm going to move from left to right, and I'm going to start generating the moment diagram. Now remember, how do we generate these moment diagram values? Well, they come from the area beneath the shear diagram, okay? So we got to keep that in mind, all right? So I'm going to do my work in red here, and I'm going to scroll on down a little bit. And so I'm gonna do my work in this kind of blank space down here. So I'm going to say at x equals 0 meters, what's the moment? Well, the moment better be 0, okay? We do not have any applied moments at this left end. It was a pin, which means it's free to rotate, which means it does not support a moment reaction. So we're going to say m equals 0 there, and so that's going to be our first point, all right? Next, we're going to say from x equals 0 meters up to 2 meters, what's happening? Well, we're going to have a change in moment that's going to be equal to the area beneath this shear diagram. Now, this is a trapezoid, okay? So we can, the easiest way to handle this is you just, calculate the area of a trapezoid here. If you're, don't remember that off the top of your head, you could break this down into a rectangle and a triangle and add those areas together, but I'm just going to use the formula for the area of a trapezoid. So that's going to be 1/2 times 103 kilonewtons plus 99 kilonewtons times 2 meters. And so that change in moment is going to be equal to 202 kilonewton meters. And so for a refresher, the area of a trapezoid is 1/2 times h1 plus h2 times the length of the trapezoid, okay? And that's what I computed down here, all right? So what does that give us for the moment at x equals 2 meters? So I'm going to say at x equals 2 meters, the moment is just that 202 kilonewton meters, all right? So I'm going to align things nicely. Here's my point. And notice when I sketch this, I'm trying to align things really nicely to be organized. So how are these 2 points related? How is this first point and the second point related? Well, this is going to be concave down quadratic. Okay, how do I know that? Well, it's because the shear diagram was linear decreasing, which means that your moment diagram should be quadratic concave down. So this is a parabolic segment, all right? What do we do next? Well, we keep on moving, and I'm going to say from x equals 2 meters to 3 meters, the change in moment is going to be equal to the area of this trapezoid. And notice that this is negative. These are negative values, so that needs to be built in. So again, it's still a trapezoid, so 1/2 times negative 20, what was the value? 201 kilonewtons minus 203 kilonewtons. Notice both are negative, times the length of it, which is 1 meter. And so we crank this through and we'll get a negative 202 kilonewton meter. And again, that's the change in moment, delta M, that area there. And so finally, we're going to say at x equals 3 meters, we'll be able to say the moment there is just 0. And of course, that makes sense because you are currently at 202, and then you decrease by delta M, which is negative 202. So here's that positive 202, and then your change in moment on that second domain is negative 202. So that's going to curve you back down to 0 there. Let me draw that a little bit nicer for us. Curve us back down. That still doesn't look very good, does it? Oh man, I'm just making it worse. It's hard drawing this on an iPad sometimes. Okay, there, that's better. So back down to 0, and I like to shade my diagrams in. And so some notes we want to make here. This is linear decreasing. This segment is also linear decreasing. And both of these segments are quadratic concave down, all right? So that concludes this example video of sketching shear and moment diagrams using the graphical method. If you found this helpful, please hit like and subscribe. Thanks for watching.